So it's 4 o'clock, but maybe we'll wait another minute or two. People are streaming in here.
Sure.
Uh, Felipe, do you wanna share your slides maybe so we're ready to go?
Yes.
I know you checked them earlier.
Mm-hmm. The wait, be the main one here. At full screen mode.
Yeah, that looks like the right one.
Okay.
All right. Well, let's see. 401. Often we'll have there'll be a lot of questions at the end. So in order to not eat into that too much, today, so Rip is occupied with another obligation, and so he asked me to introduce Felipe. So Felipe Gonzalez is going to be presenting his work today, crystallizing cores of super Earths and other planetary phenomena unraveled by first principles simulations. So, Felipe, let's hear what you have to tell us.
Okay. Thank you very much, Ryan, and thank you everybody for coming today. So what I want to present to you today is my work on my personal view on the crystallization of the cores of super Earths and other planetary phenomena that I'm going to address through first principle calculations. And the idea is that super Earths are these massive planets, more massive than Earth, but not as large as Uranus and Neptune, that are basically very common in the galaxy, but we do not have them in our solar system. So these planets are very abundant, and since they're very massive, the pressures that at which they can get in their interior they are much larger than the ones you have on Earth. So the materials that you can see here in the background uh, that are in the interior, in particular at the core, are subject to pressures that we don't see on Earth. And it means that the materials can undergo different phase transitions that we are not used to. So in my investigation, my line of research, I basically study high pressure phenomena based on first principle simulations and look for transitions, solid-solid, solid-liquid, characterization of equations of state, and I generally choose materials that are relevant for the composition of planetary bodies like super Earths and gas giants. And this really intersects very often with warm dense matter, which is when you have very high densities and very high temperatures that basically enables this thermal ionization of the atoms, and you have phenomena like pressure ionization, and that we usually characterize using shock compression. So this is all intertwined, and there's a lot of development in the recent years that can guide us through this process. So the main question I want to pose today is what can first principle simulations reveal about planetary interiors? How can we use them to say meaningful things about planetary interiors? And I want to start the motivation with our common idea of how planets form. So we all have this idea that in an accretionary disk around the star, there are these dust particles that later become pebbles that start accreting due to gravity. And when gravity is large enough, it starts a runaway accretion of even more mass, and you end up with a gigantic sphere of molten rocks, right? So we think that the initial state of almost every planet is a magma ocean, where differentiation can happen and the heaviest elements go to the center. And we really want to investigate what is the thermodynamic of planet formation. So how is that this all happens? What happens with the materials that are at the very center that are subject to pressures that were not there at the beginning? And is there a rocky core? How does differentiation happen? And is there a magma ocean? How the different elements partition? So these are all questions that have to do with the chemistry and physics of materials at very high temperatures and pressures. So we all know, I guess, here in the CMAP group, that we're motivated by the discovery of exoplanets. We have more than 5,500 exoplanets discovered so far, and they come in all types of sizes and types. We have gas giants, we have Neptune-sized planets and terrestrial planets, and in between there are the super Earths and also called sub-Neptunes, not depicted here. that seems to be very common in the galaxy. Again, there's a wide population of these two categories of planets, super Earths and sub Neptunes, and we really want to know what they are made of, right? Very interesting planetary systems have been discovered, like the TRAPPIST system, where you have seven terrestrial like planets in the habitable zone, and they're in interesting orbital resonances among each other. And people are trying to investigate now particular systems like this one, and they want to know what are they made of. So recent studies like this one have studied how the inner layers, the interior of the planet interacts with the atmosphere, and models have been developed in order to understand how degassing or trapping of different of different volatiles are trapped in the interior, and what is the interplay between these different layers at the interior with the atmosphere that we can actually detect. So all these questions motivate us to do more research into material science, right? So in today's talk, I will tell you about my most recent work on the melting curve of iron and how this can tell us about crystallization of super Earths, and talk about a bit about planetary interior models. And I will tell you a little bit about the story of Jupiter's and how we come to the conclusion that the core is eroded. Um, to continue with water worlds, which is a different category of exoplanets within the sub-Neptunes, and then a little bit of the melting line of silica and ramp compression, if we have time. So I want to start with iron and the uncertainty that currently exists on its melting point. So if you ask the community, what is the melting temperature of iron? 330 GPa, which is the inner core boundary for the Earth, they will all give you very different answers. So you can see here highlighted in red are the experiments that you can see there's a discrepancy of more than 500 Kelvin in the melting temperature, which we think it should be just one. It's just one pure material, iron, and it should have just one melting temperature. But the uncertainties are large, and their measurements have very large error bars because it's a difficult measurement. And when you ask the theorists like me, what is the melting temperature? We all also come up with different answers. People even choose different crystalline structures to start with, like the BCC structure, which we think is not the most stable structure at the Earth inner core boundary pressures. So you would get eventually a different melting temperature if you use that structure. And we also use different approaches. What do you mean by the actual melting temperature thermodynamically? How do you calculate it? This all is relevant in order to come up with this number. And my main message here is that we still cannot agree what the melting curve of iron is at really high pressure. So we really have to put more effort into calculating it and measure it. So one of the most recent experiments at the most extreme conditions ever done for iron is the measurement by Rick Krause in 2022, where they did something really cool. They basically started with a solid iron sample, and instead of just launching a typical shock, this shape of the laser pulse, uh, they first launch a shock into iron and then a ramp compression wave. So this does is the following in the pressure temperature space that I hand drew here. It basically sends iron into a liquid point in the Hugoniot that starts naturally decompressing in this experiment isentropically. And then when the ramp wave comes along, then it starts isentropically compressing the liquid from a liquid state until it hits the melting line of iron, and they observe in situ crystallization. So when they do this for different starting conditions, what they observe is in situ crystallization of the liquid iron at different conditions. And they performed these measurements at several pressures, and they were able to get and observe in situ crystallization up to 1,000 gigapascals. So we're already able to perform measurements of the melting curve in the terapascal regime nowadays. So this is really interesting. It's a very important constraint for iron, and it tells us about planetary formation. Because as I was saying at the beginning, if you start with this scenario of a magma ocean that is on top of a liquid iron core, then with time, this whole thing will end up crystallized, right? And you will have a frozen mantle and a frozen core. With the Earth, where like in the mid of the process, we still have a liquid core that will eventually crystallize if we give a couple of billion years more, right? So, in order to understand how this core crystallized, what we usually do is to calculate the adiabat of the planet and compare it to the liquidus of the different materials that these planets are made of. So, if you imagine for the core, for example, if you have an adiabat for the core, I have the liquidus of the core material, in this case, iron. The planet will start cooling down, so this adiabat will start coming down, and it will intersect the liquidus here at the highest pressures, which represents the center of the planet. So in this case, you will have an adiabat that is shallower than the liquidus, and that will induce a bottom-up crystallization because it starts from the highest pressures first, which means the center, outwards. So this is the bottom-up crystallization scenario. But if you have an adiabat that is steeper than the liquidus, like it could happen for the mantle, for example, then as the adiabat comes down, it will intersect the lowest pressures first, and then you will have a top-down crystallization. So this is more the mantle of the Earth crystallized in a mixture of the two because there's some evidence that the crystallization started from the middle with a basal magma ocean, but it all has to do with this interplay between the actual adiabat and the liquidus of the actual materials that live there, right? So in general, for building models of planetary interiors, we choose the most simple representative material, MgSiO3, that you will find very often in the literature. And for the core, people usually use iron. So these two materials are the building blocks for any rocky body, and we need very good equations of state if we want to make models that are built on this information to tell something about planetary formation and evolution. So if we look up the melting temperatures reported for MgSiO3 and iron, you can see here that in general, the melting temperature of silicates is much higher than the melting temperature of iron at any pressure. And if you imagine a mantle adiabat coming down here, you will see that it will intersect the melting line of MgSiO3 first, and way after, it will intersect the melting line of iron, which means that the mantle will start crystallizing first in some way, and then the core, right? But as I said in the beginning, there's a still discrepancy on what the actual melting temperature is at the megabar pressure range, hundreds of GPa, and we don't have a very certain equation of state of iron yet that we can all agree with. And the melting lines of MgSiO3 that have been reported have been mostly calculated with ab initio calculations like the ones I do or classical simulations. So there's still very little evidence of what is the actual melting temperature of iron from experiments. And one of the few experiments that have been performed was done by Ingwei Fei in 2021, where they shock compressed bridgemanite, which is a high pressure polymorph of MgSiO3. And when the Hugoniot intersects the melting curve, there's a discontinuity there, so they are able to locate this point. But they did not have measurements for the actual temperature. What they did was to infer it from the DFT simulations, even though they performed an shock compression experiment. So I think someone has a microphone. I'm getting total audio. Okay. Thank you. So they were able to come up with a melting line by this point that was constraining the melting line in these hundreds of gigapascal regime. And you can see here that it points towards an intersection with the melting curve of iron beyond 1,000 gigapascals. But in this whole range, again, it seems like the silicates have higher melting temperatures than iron. And when you look at another recent experiment, basically the only other experiment available by Dane Frattantuono, they started with the instantite phase of MgSiO3. They shock compressed it, intersected the melting line, and that provides another melting point because it intersects the melting line at a lower pressure. But the difference is that they did have a pyrometry available in their experiment, so they did measure a temperature, and when you put it in the phase diagram, the melting curve looks like this. This is very problematic because this melting curve for MgSiO3, with the only measurement in the hundreds of gigapascals that we have available for temperature, is way lower than any other estimate for the melting temperature of the same material performed by other experiments and simulations. And that will change completely how we conceive the crystallization of planetary interiors, because it would mean that the core would start crystallizing before the mantle. And this is something that is very unusual. Now, the question is then, is it possible that the melting temperature of silicates is lower than the melting temperature of iron? And that basically means is a core crystallizing first? That depends on whether we have reliable equations of state for these materials. So in order to address these questions, is there a question? Okay. So in order to address this question, I'm going to address today more the part of iron and how we calculate the melting line of iron. I'm giving a spoiler alert. My curve is in blue here. This is what I calculated, and I'm showing it here before I show you how I did it. But you can already see that it's kind of in agreement with like other calculations and estimates of the melting curve. And the uncertainty is not as big as the uncertainty there is between the melting curves of MgSiO3, which have like this very huge uncertainty. So the takeaways, again, before I tell you how I did it, is that most of the melting temperatures reported for MgSiO3 kind of agree and are in the higher end of temperatures, while this measurement by Dane Frattantuono points to a much lower melting temperature for the MgSiO3, which is our proxy for super Earth's mantles. So the way in which we calculate melting temperatures, at least I did it in this project, is using this tool called thermodynamic integration, which I will not go too much into the detail, so feel free to ask me after the talk is over. But what we basically do is to take something that we know analytically, like the Einstein crystal, for which we know the free energy, and we transform it slowly with this coupling parameter lambda into the fully interacting DFT system, which is fully ab initio with no approximations of harmonicity or any other similar approximations. And with this free energies, what we are able to do is plug the pressure and volume here to calculate Gibbs free energies and compare the stability, where the solid is more stable than the liquid at different pressures and temperatures. And what this approach also tells us is basically what is the entropy of each state, because having the free energy immediately allows us to know the entropy, so we can start building planetary adiabats. So after doing this, we look for the points where delta G, the difference between the free energy of the liquid and the solid, is 0. So that is by definition in thermodynamics the melting point. And that's how we find this blue marbles here. So all of these are melting points, and our fitted melting curve is in blue. And as you can see here, here's the zoomed in discrepancy in the data that I showed you at the beginning. So we're more or less within the error bars of what other people have reported, a little bit towards a bit higher temperatures in this 300 GPa regime. But overall, it's in very good agreement with the experiment I showed you by Rick Krause, where they did shock plus ramp compression. So that was really encouraging because it shows that this approach really works. Just based on first principles, it's just pure iron, parent energetics, and we get the melting point, the melting curve. And we reported this in Physical Review Research last year. I invite you to download a paper and the equation of state. We published all our data and it's accessible. So as I was saying, with the free energies that we get at every single pressure and temperature, we can calculate entropies and then interpolate where this entropy stays constant. And that's for us an isentrope of the material, which is representative of an adiabat of the core, right? The core, we believe it's convecting. So a convecting material is represented by an adiabat, which is just pure iron in this case. And the first thing we can see is that the melting curve is steeper than the adiabats, which puts us in the first scenario of bottom-up crystallization. So that was not clear at the beginning, at least not evidence, that even in the thousands of gigapascal regime, super Earths would crystallize in the same way as the Earth did, which means bottom-up crystallization. And then we really wanted to build a model and to tell something about how the cores actually crystallize. So in order to put a planetary model together, you need like a few ingredients. First are your layers. You assume a layered planet with an iron core and certain silicate materials. As I mentioned, MgSio3 is our favorite. And then you have to solve certain differential equations. You have the equation for the mass contained a certain volume that depends on the density. And then you have hydrostatic equilibrium with gravity. And then the crucial equation that completes this set of differential equations is the equation of state that we know is unique for every material. We generally can obtain it from experiments and models, but in our case, we obtain it purely from DFT simulations. So we have an equation of state for iron. We have an equation of state for silicates that we borrowed from previous projects that we did. And these models look more or less like this. So if you have a fixed mass of the planet and a fixed radius, then what you obtain is basically a profile for the pressure as you get deep down to the planet. Here's the surface, and all the way to the interior, radius equal to 0 is the center. You have the highest pressure. And here you can see the jump in the density where you have the iron core, and here's the mantle with lower density. And these models have some free parameters. For example, the core mass fraction here, how much of the core in terms of mass has the planet for a given mass and radius. And the fact is that if you vary the core mass fraction for a fixed mass, say 5 Earth masses, then as the radius starts increasing, as a core mass fraction starts decreasing, then the planet radius starts increasing. And also you can see that the pressure at the core mantle boundary increases because you're mostly, the core mantle boundary here is almost at the surface with a lot of iron here, while here is very deep down in the planet, almost at the center. So the pressure at the core mantle boundary is higher. This means that basically at a given mass here, 5 Earth masses, and a given radius, you have a certain boundary for the central pressure and the core mantle boundary pressure. So those will be two limiting values that we'll take to build our models. So with these two values, for example, in the pressure temperature phase diagram, what we will see is the following. If you imagine, again, an adiabat coming down, intersecting the melting line, say for a 5 Earth masses planet again, it will intersect the center pressure at the whatever melting temperature is at that pressure. And that will start the onset of crystallization from the center of the planet. And the pressure that indicates the core mantle boundary will, when it reaches, the adiabat reaches this point, it will mean that all the temperatures are well below the melting point of iron, which means that everything will be frozen. So with these 2 points, we can place boundaries on when the core crystallization of a super Earth will start and finish. And if we look at models reported in the literature, you will generally see models that suggest very low pressure, temperature values like 5,000 and not much more than that. But with our model, what we found is that you actually need temperatures well beyond 10,000 Kelvin to maintain the entire core in a liquid state, which means that if you assume that the core is made just of iron, super Earths will have frozen cores unless you have temperatures that are way higher, like 10,000 Kelvin or more. So that was a striking surprise because we don't know if the super Earths can actually stay that hot for the entire lifetime. And that will mean that probably they will not be able to generate magnetic fields from an liquid outer core because the pressure makes the melting temperature increase so much that it's not compatible with a liquid outer core. So I was happy to see that Sarah Seeger from our CMAP group recently used our melting curve to put together models for planetary interiors and discovered that most high density exoplanets are actually unlikely to be remnant of giant planet cores. I must confess that I still haven't read the paper completely, but it looks very interesting and I feel very encouraged by the CMAP collaboration. So that's all I wanted to say about iron. And I want to switch gears now and talk about Jupiter. So Jupiter is a different category of planet, of course, where we have much more gas. Uh, and we believe that it's surrounded, there's a rocky core surrounded by metallic hydrogen below the layers of hydrogen helium mixture with an intermediate layer where helium rain occurs. And the conditions at which this center of Jupiter it's subjected to are around 40 megabars, which is 4,000 gigapascals and a couple of thousands Kelvin. And the question we posed was, is it possible that the metallic hydrogen in Jupiter is able to dissolve the rock that basically formed the planet by accretion? So in order to address this question uh, of can metallic hydrogen dissolve the core, we did a little bit of chemistry. This is very similar to what I already showed you in the crystallization of super Earths. We need Gibbs free energies, but here the question that we put is different. We are after the solubility of a representative rock in this planet. We chose silica for simplicity. And we want to know if it's possible to generate this reaction where you have a certain number of hydrogen atoms in the metallic phase interacting with SiO2, a rock, and you can get a dissolved state of this stoichiometry. So basically, we're imagining boxes like this where there's metallic hydrogen and around the rock that is way more abundant than the rock itself, and it ends up in a more stable state where the entire rock is dissolved in this metallic hydrogen. So the reaction that we're looking for is this Gibbs free energy of solvation, where here you have the free energy of the dissolved system on the left, and you just subtract the free energy of the parts. And the main takeaway here is that if this delta G is negative, then the system dissolves. Basically, because it prefers energetically the dissolved phase. It will have a lower free energy than its components. So again, we employ the same technique that I showed you earlier, thermodynamic integration to calculate the Gibbs free energy of each of these phases for every term that I showed in this equation. And what we found was basically that for all the interior conditions of Jupiter and Saturn for mental boundary pressures and temperatures, the dissolution is favored. Basically, beyond 5,000 Kelvin at mostly any concentration, you have that the dissolved phase is preferred energetically. So it would silica would dissolve almost at any concentration when surrounded by metallic hydrogen. And in our group, other members of our group have studied other materials like magnesium oxide, iron, and water, and they also dissolve in metallic hydrogen. So we believe that metallic hydrogen is actually a very good solvent of rocks at these conditions, but not at lower temperature conditions, for example. So this has changed the picture that we have of the interior of Jupiter over the years, where rather than a compact core surrounded by the metallic hydrogen, what we believe is happening is that you have a dissolved core at the very center that can expand almost to half of the planet, like 50% of the radius of the planet, and then comes the metallic hydrogen layer and the gases on top. And these models of Jupiter have been confirmed by recent experiments, measurements by the Juno probe that is orbiting around Jupiter. And Burkhardt and his collaborators from the Juno team published this paper that indicated that these gravitational moments that have to do with the distribution of mass density inside the planet imply necessarily a dilute core. So it's an indirect evidence that the solvation of the core could be one of the explanations why you have a distributed mass within the core of Jupiter. Okay, so now I want to tell you a little bit about other types of planets, which is what we call water worlds. And water worlds can be considered as a subcategory of sub-Neptune planets. The distribution of densities of the exoplanets that have been discovered suggests that some of them have a considerable amount of water. And when you think that how much water there is on Earth, it's just a very teeny tiny layer on the surface that makes the oceans, but most of the Earth is just rocks and iron. In these planets, we believe that there could be probably 50% in terms of mass on the content of water ice or other ices to understand the radius that these planets have. And what I was telling you 2 minutes ago about the distribution of super Earths and sub Neptunes, it seems to be this bimodal distribution of exoplanets where the super Earths and sub Neptunes are very popular in the galaxy, but again, we don't have them in our solar system. And we really want to know what they're made of, what is happening at their interiors, because it really seems that the composition of these planets is really different from anything we know in our solar system. So we pose the question in the following way. If you have a very significant amount of ices, or water ice in particular, on top of a layer of silicate, is it possible that at these conditions, very high pressures and temperatures, the silicates and water mix? And we pose this question because at very high pressures, we know that hydrogen, the water molecule, does not exist anymore because water becomes superionic, and the hydrogen atoms start flowing like a liquid in the lattice of oxygen atoms. So we do not expect that the interaction between what we call normal water and rocks is the same at these conditions, because you're interacting superionic water with rocks, or very high temperature liquid water and high pressure liquid water with rocks. So we conducted some preliminary simulations in collaboration with Sarah Stewart, where we did some smooth particle hydrodynamic simulations. This was a research led by Tanya Kovacevic in our group. So we basically ran the simulations of collisions between two different water worlds with layers of water, silicates, and iron to see what pressures and temperatures we could expect in formation events like this one. And we started exposing this water and ice to different pressures and temperatures to see what happens chemically with our simulations. So what we did was literally to put water on top of rock, in this case, H2O, and our favorite rock, MgSio3, and just observe what happens. So if you let these simulations run, what happens at really high temperatures is that you melt both materials, and when they are molten, they become readily miscible. At these conditions, they form a homogeneous mixtures of the magnesium in green, oxygen in red. The other oxygens are in blue or purple. And there's a high mobility of the hydrogen atom. So everything is a homogeneous mixture at these conditions. Of course, when we simulate at very low temperatures, everything stays solid and the water stays unmixed with the rock. They're both like stable solids. Then when water becomes superionic, actually, it stays stable as superionic water on top of rock, and they don't mix, and no protons merge with the rocky structure, they don't go into the lattice. Then we increase the temperature even more, and we observe that the water melts and stays completely liquid and still doesn't mix with the rock MgSio3. And it's not until you reach temperatures higher than the melting temperature of MgSio3 at these conditions that they become like fully miscible at all these conditions. So again, this has reshaped the way we understand planetary interiors, because we think that rather than having separate layers, it's more likely that you will have a layer of a gradient of compositions where these materials become miscible because the temperature allows for miscibility at these conditions in these water worlds. And very, very briefly, I want to tell you also about ice giants. And this is an investigation that Kyla Davila has conducted with us in our group, where she found that many planetary ices, which means combinations of hydrogen, carbon, nitrogen, and oxygen, exhibit this doubly superionic behavior, where other elements like nitrogen atoms can flow almost in the same manner as the hydrogen atoms throughout all the lattice. So there's a second species that becomes mobile and has diffusivity, while the most heavy species remains in a stable lattice as a solid. So I think this can shape the way we understand also ice giants like Uranus and Neptune, and we have to reconsider the materials that undergo these phase transitions, because they can change the way, for example, heat is transported um, from the interior to the upper layers of the planet. So here's just a little depiction of how the mobility of the hydrogen atoms cover the entire lattice, and then when it becomes doubly superionic, then the nitrogen atoms are start moving throughout the entire lattice too. Okay, so we have covered three types of planets and different interesting phenomena that occurred inside them. And now I want to turn to a specific calculation that I want to tell you about, which is related to the melting curve of silica. And this is more to highlight the ways in which we calculate melting and what we mean by melting. So I already told you that we calculated melting temperatures with the Gibbs free energy, and the point where the Gibbs free energies of the solid and the liquid are equal define a melting temperature, right? But actually calculating Gibbs free energies is very difficult, especially in ab initio simulations. You have to do particular implementations in your codes. It's not readily accessible. So it's not that straightforward. So other people use other methodologies like the coexistence or two-phase simulation method, where they literally put a solid in front of a liquid, and at a fixed temperature, they just allow it to either crystallize completely or melt completely, and that will place boundaries on the melting temperature. And the more simulations you do, the better your constraint is on the melting temperature. Now, there's another alternative, which is the Z method, that is actually not thermodynamically justified, but I think it's worth a try because it has been shown that for many materials, it predicts the melting temperature accurately. So I decided to give it a try. And this is a method that is very simple for two reasons. First, because it's a single phase method, you don't need two phases. And also, you don't need to calculate free energies. So it's a very promising method to calculate melting points of material. And it's based on this idea that if you heat the material at constant energy, which may be something weird for experimentalists, I think, to think about. But if you preserve the energy, then is the pressure and the temperature that changes during your simulation. And there's a point where you increase the energy of the material that stays fixed the entire simulation after fixing it, that will land precisely on the melting point. So you will observe during your simulation that the sample starts melting while the energy is constant, and the pressure increases, but the temperature decreases. And it decreases precisely to the melting point. So you form this type of Z curve in the pressure temperature space. And this bottom part of the Z curve is actually melting point. So I did this for SiO2, and it seemed to work really well. I predicted a bunch of melting points. So for each of these points in this curve is an associated Z curve on top. And uh, basically, with this study, I was able to conclude that silica up to the thousands of gigapascals stays well above the core mantle boundary pressures and temperatures of Jupiter, Saturn, and super Earths. So if we find it there, it should be in solid state and not in liquid state, which is important to start building models that use information about the equation of state of these materials. In addition, if we zoom in here in this lower pressure part of the phase diagram, you can observe that it agrees really well with experiments that were conducted by Marius Milhaud and collaborators in 2015. And they predicted actually that they encounter a conducting phase when they melt silica at hundreds of gigapascals and thousands of Kelvin. So the predictions from this very simple method agree very well with the reported experiments for the melting curve of iron. But there's still a lot that we can do to improve our predictions. And there have been cases where this Z method has shown to just not work at all. So there's, in terms of methodologies on how to detect melting, I think it's really worth trying and investigating this method more in terms of investigating its validity. So, well, already mentioned that. And the final thing I wanted to mention to wrap up is something that I will discuss very briefly because I already presented this, I think, 3 years ago in a on previous CMAP seminar that I was invited to, which is this issue with ramp compression that we try to model with first principle simulations. And ramp compression is very important because it's this technique that have been developed by experiments, especially in Rochester and Livermore, where you can design the laser pulse in a ramped way such that it can prevent the formation of a shock. So you avoid melting and you can reach much higher pressures because you deliver all the energy into compression and not into heating. And pressures up to 5,000 gigapascals have been reported for diamond in a more recent experiment by Amy Lazicki, up to 2 terapascals, that's 2,000 gigapascals. They tried to detect this new phase of diamond, which is the BC8 phase that should occur around 1,000 gigapascals, but still there is no evidence, no clear signature of this BC8 phase to date. And we really don't know what's happening. So we need to investigate diamond a little bit more. We need to have a precise equation of state and X-ray diffraction data in order to see if we really understand the equation of state of diamond well. And we put this model that I will not discuss into details today, but feel free to reach me and download the paper here and publish it in PRB. It's based on uniaxial compressions of diamond and trying to get this inner energy into heating. And as you can see here, our model predicts a curve that is well below the shock Hugoniot of diamond, but is actually not as shallow as an isentrope. So we have some plastic heating here that is modeled indirectly, is a result of the simulation. And it's a reasonable result because it stays below the melting temperature of diamond at all pressures reported. But we had a really hard time matching the actual densities and stresses reported in the experiments. And we tried to compare it with a multi-shock scheme where you have not only the principal Hugoniot, but a secondary, tertiary, and so on and so forth. And it matches really well with that model. But again, both are based on ab initio simulations. So it's just a proof of concept that within the simulation, it makes sense, but it still lacks of validation. So I really encourage experimentalists that are doing ramp compression to try this model and see if we can develop something probably even better. Another interesting fact of this model that we put together is that we can compare it with models that try to come with estimates for the plastic heating that occurs in the sample. And in these models, they usually introduce Taylor-Quinney factor, like in these experiments by Amy Lazicki, appears in equations like this, where you have to assume how much heat, plastic heat, plastic work goes into heating the sample. And you will find very often in the literature that this factor is 1, which means like 100% of the plastic work goes into heating. And what we're finding here is that you actually need something like 0.25. So 1/4 of the plastic work is absorbed by defects, probably, or something like in that sort of line of reasoning would be the explanation. Because if it's 1, then you get way more heating and you go well above the melting curve of diamond. So this is again to encourage experimentalists and we theorists to develop better models in order to understand this, because we really don't understand what's happening here. And I just finally wanted to mention that this initial estimates for plastic work in diamond by Bradley et al. In ramp compressed diamond were pointing towards a much higher temperatures during the ramp compression experiments, even though it was similar to these models based on the Taylor-Quinney factor. So that's all I wanted to say today. I just really want to acknowledge the center and my funding sources, my group. I work with Burkhard Militzer here at Berkeley, previous collaborators here that you're probably familiar with. And I leave you with my conclusions there, and feel free to ask any question. I would be happy to answer, and send me emails as well. That's fine. Thank you very much.
Thanks, Felipe. Excellent talk, covering a lot of ground there, and I guess some not ground.
That's what I
Yeah,
try.
so questions, and let's give students and postdocs the first option here. Well,
Uh, Hi, Felipe. I had a question actually.
Sure.
yeah, go ahead, Dylan.
Um, yeah, I thought that was a really interesting talk. Thank you. I had a
You
question about your simulations on it was the H2O and MgSiO3.
okay?
I was wondering, did you uh did you try liquid H2O with solid MgSiO3? Did you see any like uh mixing results in that scenario?
Let me go back to it. So this one. So you say liquid water and solid MgSiO3?
Right, yeah.
Yeah. So this is this section here, the triangles. So basically, there was this interval where we exceeded the melting temperature of superionic water in that case, right? First goes to superionic, then it melts, and it just stays there, molten with the rock, and it does nothing to the rock. The rock remains stable, and we had this coexisting simulations of like stable liquid H2O, which is non-molecular, it's atomic now, and the MgSiO3, which just stays um, solid as it should because it's below the melting point. So yeah, we do have them, and we don't see like any miscibility. And we even try to force a hydrogen atom, a proton, into the structure, and it literally the structure exposed this proton, and there was no way to make them miscible, at least by brute force.
I see. Yeah, thank you for the clarification. And then also, I was just curious for the simulations where they
Mhm.
were fully miscible. I was just wondering, like, um, how long you ran those simulations for.
Oof. That's a number that I should remember, and I don't remember on the top of my head. Tanya did all the simulations, and if they last, I think, beyond 10 picoseconds. And that's like what's the minimum requirement for us to say, okay, it's like this is enough to, when we see the cell already like mixed like this, we observe the distribution of ions. And if it's like homogeneous like throughout the cell, we say, okay, this over is no point of simulating longer. But yeah, way longer than a bit longer than 10 picoseconds.
Gotcha. Okay. Yeah. Thank you.
I see there's some hands up. Are there any other questions from students or postdocs? And of course, you can chime in later as well.
Well,
Yeah.
Stefanos is student, right?
Yeah,
Oh, there you go. Yeah, Stefano. Yeah.
Yeah. Thank you so much for the presentation. It was really interesting, actually. I have a question about the solvation of hydrogen and rocks.
Okay.
And yeah, I wanted to understand how it really happened because yeah, if you think about chemistry, you usually would expect that the similar substance would with each other, so polar with polar and apolar with apolar. Here you have hydrogen that is apolar, that is solvating something that is polar, like SiO2, magnesium, and so on. So the solvation mechanism doesn't seem to be really electrostatic or like not really the solvation as we might think as like at room or ambient conditions. And I wanted to better understand what was the driving force or if we should think differently about this solvation.
Well, I think it's really worth to think of it differently because I know you come from a chemistry background, I come from a physics background. I don't think of these things in terms of are they polar or not. I am actually not even sure. Is metallic hydrogen polar?
I would say
I wouldn't.
apolar.
Apolar, right?
I would say
So
because yeah, while
okay,
SiO2 would say that is polar.
right. So that would,
That's the
I guess,
feeling, but yeah.
yeah. But I would not. I am not really sure. Like, what's the mechanism behind it? Because I have this supercells of interacting atoms that move and have a well-defined energy, and we're just comparing the energetics, right? We're saying, is this reaction favorable in terms of the energetic, in the same that you would think, like an ambient conditions, like enthalpic reaction would be possible or not. We're not saying what are the mechanisms that lead to this. We're just like talking about the energetics. So we don't really know like what are the possible reaction mechanisms, and nor we know the reaction rates, for example, for this reaction. And then that part of the chemistry we did not investigate. So we would have to just like dig into our simulations and investigate further. But yeah, I wouldn't have an answer for you in that regard.
No, it's okay. It's okay.
No, but I think
okay.
for CMAP people, we should be able to bridge the divide here, if I may interject. And the reason is, it comes back to this definition. When you come from your background, you talk about a polar and a non-polar substance. So polar substance just means there's somewhere there's a charge that's positive and there's some of this charge that's negative. And then a non-polar means it's not. And I agree with you. At one bar, there's a strong tendency for these two types of materials not to mix. I think when chemists invoke this, there's usually always a band gap. For polar and non-polar substances, they're not metals. If you talk about metals, I don't
100%,
think these.
Yeah.
So therefore, when Philippe is metallic hydrogen, I think we're in trouble. So this answer was right. But I think both of those things are non-metals. Sorry.
Thank you.
Okay. Okay, so probably it is more like mercury melting gold or something like that. I try to find an analogy, yes, at room temperature, just to understand. Okay, that's good. Thank you so much.
All right, Eric.
Let's see. Yeah, so thanks, Jeff. So I was just going to ask in the earlier part of the talk when you were describing the high temperature for melting of the core, if of the terrestrial super Earths, if you have any implications for of the same, of your calculations for the survival or the onset of the basal magma ocean.
Mm. Well, for the magma ocean, what is fundamental is what I did not address, which was the equation of state of Mg-SiO3. So yes, let me see what's the best diagram to talk about this. That's one. Yeah, something like this, right? So if you imagine, this is just like I hand drew this mantle adiabat, and I think this is what people believe the actual mantle adiabat for the Earth looked like when it intersected the melting curve of silicates. Uh, it intersects at a point that is nor the center nor the top. So that would start the onset of crystallization of the magma ocean. But I'm not deriving here the melting line of Mg-SiO3. That's actually a project I have on hold, and I really want to characterize more. But we first have to have a good mental adiabat, and also we have to have a good melting curve for Mg-SiO3. And I just wanted to like open the questions that we have this huge discrepancy on the melting curves already. So depending on which one we take, we get a completely different scenario. So I did not investigate this part in particular because I was focusing on iron, but I think it's a endeavor worth pursuing.
Excellent, excellent, great. Yeah, thanks. Excellent.
Let's see, other questions? So I guess returning to this miscibility question. So Felipe, is there a rule of thumb which you can use to anticipate if two materials will be miscible or immiscible? Is there some order parameter or something you can use to estimate? You know, the polar nonpolar might work at 1 bar, but is there something that you've identified or have thought about?
This is something I am really interested on, like looking into more details. We have not developed models to understand like miscibility. We just like go for the simulation and do it and see what happens. So I think something like that will come up, at least in this regime, once we have like plenty of simulations and varieties of different materials interacting. But I don't have like an intuition right now to say like which materials will become miscible and which not. We already did it with MgO, which is a similar rocky material, and we observed something slightly different, which was that it starts mixing below the melting line of MgO, and we're now trying to calculate the energetics and actually take the free energy approach to see like if the phase is thermodynamically stable. But in terms of developing a model that tells me with an order parameter when they will mix or not, I think we're very far from that. But I would very much like to get into line of research.
Work on that.
Yeah. Let's collaborate.
Well, there will be a talk on this next week, right?
Oh yeah. Yeah.
The answer is no. We have no idea. We have no idea. Every material seems to be different, and I will show you one next week.
All right, let's see. Let's see. Other questions? Well, maybe I'll add another one then. So you talked about this Z method. You know, when you're calculating the melt. So I guess what you do, you have a box at fixed energy and allow it the pressure temperature to change. And it looked like you were going up, like so you were pressurizing it. Do you get the same result? Is there a hysteresis if you relax it? Do you get the same? Do you get or do you get a supercooling?
That's a very interesting question, and I think it doesn't work like the way you expect. Oh, so am I sharing again? The right slide.
Yes.
Okay. So the problem is that if you start with a liquid, because of how molecular dynamics works, you generally end up with amorphous. Because if you start decreasing the energy, that like technically mean during the simulations that you set a different initial temperature. So it's basically like spontaneously trying to freeze the liquid, and the liquid doesn't have like enough time to like move the particles around, and it just stays frozen. So I cannot observe, starting from a liquid, a complete crystallization, because just the atoms just freeze in this method. So there's nothing useful I can get out of the simulation.
Well, but I
Because the
guess
way
isn't
it
that
works.
freezing? I mean, that's melt? Isn't that melt? How's
I
that
mean,
different?
if you imagine the last picture here on the bottom right,
Mhm.
that is a solid evolving into a liquid, right? Because it has too much energy, it cannot maintain the crystalline structure stable at that energy, so it has to transform into the liquid. And then these particles are like traveling around. They have diffusion. But if I take that liquid then and I reduce the energy, it
Sorry,
basically
I thought these were
spontaneously,
fixed energy
every time
calculations.
every time I change the energy, what I mean by that is I change like the instantaneous temperature,
Okay,
right?
okay, got
And
it,
then
got it. Right, yeah.
yeah, thank you
Thank you.
for the
Yes.
question.
Yeah.
Important to clarify. So the way you technically do it is you just like initialize it at a given temperature, and then the temperature changes and evolves and reaches a equilibrium value. So if you take a liquid and try to change the energy, basically what you're doing is like reducing the velocities to set the initial temperature differently. But if you do that with a liquid, they just stay frozen and they don't move. So the method doesn't work. So there's no hysteresis.
Okay. Okay. Well, let's see. So thanks again, Felipe, and
Mm-hmm.
thanks for all the questions and your attention, and
Yeah.
have a great weekend, everyone.
Yep. Thanks for coming. Thank you. Bye-bye.